Welcome to the second day of 4.4's Factoring Polynomials. In our first day, we talked about always trying to first check to see if we can take out a greatest common factor. That's a really good way to begin things. And then we looked at some special examples, like sums and differences of cubes. When those situations arise, we can factor into a binomial and a trinomial. The binomial will give us a solution, an x-intercept, and the trinomial will never factor without giving us imaginary roots. Grouping doesn't always work either, but when there are four terms and we can't take a greatest common factor out of everything, it's worth it to see if we can piecemeal it. Can we take a factor out of the first two terms and something else out of the second two terms? And when we do so, is what's left behind in the parentheses the same? If it is, then grouping is a great choice. Today we're going to talk about the quadratic form, the factor theorem, factoring polynomials completely, and then we'll look at a real-life application. As we get into day two's work, I just want to point out that these are special examples of factoring. These don't always work. In day one, we were looking at the sums and differences of cubes. We were looking at grouping, and those methods don't always work, but when they do, they're great time savers. At first glance in example 4, you see that we're dealing with 6x to the 4th, and we're also dealing with 25x to the 8th. These are higher degree polynomials, but the question is, do they factor as though they were quadratic? Can we take our work with quadratics, with parabolas, and apply them to higher degree polynomials? So in example A with this trinomial, the AC method would say, let's talk about A equaling 6 and C equaling -5. If we multiply those together, we get -30. And when we add some combination of things that multiply to give us -30, we also want to get that middle term of 7. You can think of 1 and 30, 15 and 2, but the combination that's going to work is 10 times -3, because 10 plus -3 gets us to 7. Now, with those four terms, we can talk about grouping. In the first set of terms, 6x to the 4th and 10x squared, they're both even, and they both have at least x squared. So factor out 2x squared. What's left inside the parentheses is 3x squared plus 5. Grouping only works if when we deal with the second set of parentheses, we also have 3x squared plus 5 inside the parentheses. We want inside the parentheses to be identical. Now you might notice the one difference here is that those third and fourth terms above are minus 3x squared and minus 5. So the way to work this is to factor out a -1. So I had already typed in for you the minus sign, but just note we factored a -1 out from inside those two terms. Now, when we finish up the grouping, we take what's outside of the parentheses, the 2x squared and the -1, and we group them together, and then 3x squared plus 5. So we don't come down to linear factors. Those are both quadratic, but that x to the 4th trinomial was able to be factored. In example B, we have 25x to the 8th, and we have -49. And when I look at those, what jumps off the page to me is that 25 and 49 are both perfect squares. Could we factor this? Could we get this binomial to be a difference of squares? Well, it is if we have that x term to be a square. Can we rewrite x to the 8th as being x raised to something squared? Well, powers raised to powers get multiplied, so inside those parentheses we would have to say that that was x to the 4th all squared. If that's the case, then 25 is a perfect square, 49 is a perfect square, and x to the 8th is also a perfect square. So just to rewrite that binomial, we can take the first term and express it as 5x to the 4th all squared minus 7 squared. And then a difference of squares factors in ways that we have done before. We would wind up with 5x to the 4th plus 7 and 5x to the 4th minus 7. So we're taking something that's to the 8th degree and we're still able to factor it. A core concept in this section is the factor theorem. A polynomial f of x has a factor x minus k if and only if, when we take the function and plug in k, we come out with a 0. So here's just a relatively simple quadratic written in standard form. If we factor that, then in factored form, we find out that x plus 2 and x minus 3 are factors. Written that way, x plus 2 and x minus 3, those are known as factors. If we were to go just a little bit further, we could say 0 equals that same set of parentheses. And so that's how we go about finding our zeros. Why do we call negative 2 and positive 3 zeros? Because we come up with those values when we set the function equal to 0. So go a little bit further, we find out that x equals negative 2 and positive 3. And so we have the zeros leading us to what are our solutions. Well, where do these points exist on the coordinate plane? We have points at negative 2, 0 and 3, 0. So we can talk about the zeros being synonymous with the solutions being synonymous with the x-intercepts. They all come from the factors. In this case, x plus 2 leads us to negative 2 being a 0, being a solution, being an x-intercept. Same discussion with 3. It's really a vocabulary understanding. Example 5 has 3 parts. Can we determine whether x minus 2, x minus 3, and or x plus 8 are factors of this function f of x equals 2x cubed plus 11x minus 43x minus 24. In other words, what we're asking is, does this function cross the x-axis at positive 2, positive 3, negative 8? Since it's cubic, we should anticipate at most 3 zeros, so it's reasonable to check these out. Also, the fact that 2, 3, and 8 all multiply into 24 means that they're good guesses. So let's check out x minus 2, and let's use synthetic division. Remember, when we set up synthetic division, if we want to check if x minus 2 is a factor, then in the box over on the left, we're going to put in a positive 2. We set up our coefficients and our constants, so the 2, 11, negative 43, and negative 24. I hope you can check out the function and see where they come from. We bring down the 2, we multiply 2 times 2, and we place it under 11. We add and come to 15. 2 times 15 equals 30. We add those and we come to negative 13. 2 times negative 13 is negative 26. And when we add, we come to negative 50. So our question, is x minus 2 a factor? It is not, because when we plug 2 into the function, we don't come out with 0. However, not everything is lost. Even though we're trying to find zeros and we were unsuccessful, what we did find is that when we plug in 2, the remainder is 50, and so 2 comma 50 is a point on our graph. The function looks like this, and I see it does have this nice cubic shape, and I see that it does cross the x-axis 3 times. 2 was not successful, but we're still asked to check out x minus 3 and x plus 8, so let's continue on working with those. So in part A, x minus 2 didn't prove to be a factor, but we did find that 2 comma 50 is a point on our graph. Now for part B, let's take a look at x minus 3. Synthetic division, we set up the exact same way. This time we'll put 3 in the box, bring down the 2, multiply 3 times 2 is 6, 11 plus 6 is 17. 3 times 17 is 51. 51 and negative 43 is a positive 8. And 3 times 8 is 24. That looks terrific because negative and positive 24 add to give us 0. So x minus 3 is a factor. Why? Because when we plug in 3, we come out with 0 as a remainder. So 3, 0 is a point on our graph. Now, here's a nice thing about synthetic division. We're asked to also check x plus 8, and because we already found that 3 works, we can just begin right where we ended and try the negative 8 going right here. We don't have to go back to the original. We can plug negative 8 in with the 2, 17, and 8. We can bring down the 2, multiply times negative 8, get negative 16, add and get a 1. Negative 8 times 1 is negative 8. And second time around, we also get a remainder of 0. So that's wonderful. It tells us that x plus 8 is also a factor, because when we plug that in, we come out with 0 as a remainder. Now look at the last numbers that wind up our quotient, 2 and 1. That tells us that 2x plus 1 is also going to be a binomial factor. If we went to solve that by subtracting the 1 and dividing by 2, we could come out to x equals negative 1/2. Or if you want to try the 1/2 in with synthetic division, you can. So when we go to graph this cubic again, it's the same function as we looked at in the last time around, but we do see that it crosses cleanly by the x-axis at negative 8, at negative 1/2, and at positive 3. That negative 50 is still a point on a graph. It helps us to get a little bit more accurate, and from the very beginning you might be able to tell that that y-intercept is at 0, negative 24. So we found our 3 zeros, our 3 linear binomial factors. I know as we work through that last example, it looks a little bit different than on your page, but I wanted to show you how to do it with the factoring alongside the synthetic division. At any rate, here is a more precise replica of what's on your worksheet. If you want to just take a moment to copy these down to make sure that you're understanding. In example 6, can we factor a polynomial? And maybe to say that better, can we factor a polynomial further? Both of these examples have 4 terms, and it doesn't look like we can pull a greatest common factor out of anything. So we're tempted to think that grouping might be a good method. So let's consider that. Let's look at the first example, A, and the first 2 terms are 3x cubed and x squared. Looks like we can take an x squared out of both. What we would be left with is 3x plus 1. And so I wonder, do 48x and 16 work similarly? If we can take something out, could we be left with 3x plus 1? As a matter of fact, we can. We can factor out a negative 16. So keep in mind when we're grouping, if we're able to have the same set of parentheses duplicated, that allows us to then group what we have pulled out together. So x squared minus 16 and 3x plus 1 would be a good way to factor. When we look a little bit more closely at our first binomial, we see x squared minus 16. That's a difference of squares, and so that factors into x plus 4 and x minus 4, and we still have the 3x plus 1. The beautiful thing here is that we've taken a cubic and we have found 3 zeros. Well, we've found 3 factors so far, and if we set these equal to 0, we could determine that this cubic is going to cross the x-axis with solutions of negative 4, positive 4, and negative 1/3. Following suit over on the right-hand side, 20x to the third and negative 15x squared, 5 goes into both of those, and so x squared also can be pulled out. What about the 8x and the 6? They're both even. It feels like we could pull a 2 out. Well, when we do that, our parentheses are 4x minus 3 both times. That's terrific. So 5x squared plus 2 can be bulked together, and 4x minus 3. It's tempting to think that we can do something with the 5x squared. If you compare the two final solutions here, it would have been nice had we been able to take that first set of parentheses and get us into binomials that are linear. But if we set 5x squared plus 2 equal to 0, we would subtract 2 and divide by 5. So negative 2/5, that's not a problem, but when we take the square root, we would wind up with imaginary roots. So it's okay to leave it just like this. Two more examples. Can we factor completely? In example A, 4, 8, 100, and 200 are all divisible by 4, and each of those 4 terms have an x in them. So let's make our lives a little bit easier by factoring a 4x out first. Now that's complete in terms of the greatest common factor. We can't take anything else out, but the 4 terms leads us into the thought of maybe grouping is going to work. And remember, this is a special situation. In 4.4, we're looking at certain situations that sometimes work. I'm not saying that 4 terms always lead to grouping, but it's at least worth checking. From the first 2 terms there, it seems like an x squared can come out, and from the second 2, the 25 and the 50, clearly 25 goes into both, and if we factor out the negative, that should be able to give us the same set of parentheses, x plus 2. We group together what we have pulled out, x squared and 25, and if you're paying attention, we recognize that x squared minus 25 is a difference of squares, and so we should be able to break that down into 4x times x plus 5 times x minus 5 times x plus 2. Something that is quartic, the leading term is raised to the 4th power, we should be able to at most have 4 zeros, and these will be at the origin at negative and positive 5 and also at negative 2. Our second example is also raised to the 4th power, so I wonder if we're going to have 4 zeros here. It seems reasonable to assume it's something to shoot for. I don't know if we're going to be able to achieve that. Again, it doesn't look, not every term has an x, not every term is even. It doesn't look like there's a greatest common factor for all 4 of these, but we can take an x cubed out of the first 2 terms and be left with 2x plus 1. And then, because grouping is my goal here, I see that 128 is twice as much as 64. So if we factor out that 64, both sets of parentheses are 2x plus 1. So we group together the x cubed and the 64. And if we are going back to day 1, you should recognize that x cubed is clearly a perfect cube, and 64 is 4 times 4 times 4. So we have a sum of cubes. We can break that apart into our binomial and trinomial, x plus 4, and then the trinomial is x times x, and x times 4, and 4 times 4. And then when we go to apply our signs, if it's a sum of cubes, we are going to have the same opposite and always positive. We're going to have a plus sign, a minus sign, and a plus sign. We're left with x plus 4, then that trinomial, and then 2x plus 1. X plus 4 tells us there's a 0 at negative 4. 2x plus 1 tells us there's a 0 at negative 1/2. And remember, if we try to deal with the trinomial, it won't factor. We can use the quadratic formula. When we do, we're going to get 2 imaginary roots. So this quartic is going to have that nice W shape, if you will, but only twice will it intersect with the x-axis. Finally for today, a real-life application. During the first 12 seconds of a roller coaster ride, the function g of t equals 2t cubed minus 19t squared minus 25t plus 42 represents the height in feet of the roller coaster after t seconds. How long is the roller coaster at or below ground level in the first 12 seconds? And here's a hint. The roller coaster begins at time 0, but the cubic goes from negative to positive infinity, and one of the zeros is negative 2. That doesn't make sense in the context of the roller coaster ride, but for this polynomial, it does cross at negative 2. So let's use some synthetic division. We set up with negative 2 in the box, and then our coefficients and constant. We bring down the 2, we multiply, and we add. We multiply -2 times -3, we put it under -25, and we add. -2 times 21 is -42, and we wind up with 0. Now that may not seem like it was necessary because we were already told that it was one of our zeros, but here's what this allows us to do. We can take that same function and we can rewrite it as the binomial times the trinomial. The -2 worked, so the factor is x plus 2, and the trinomial are those three numbers that are below the division bar, 2x squared minus 23x and plus 21. If I look over at those red and blue numbers on the right, we could use the AC method, multiply 2 times 21, get a product of 42, and then we want to ask ourselves what also adds to give us -23, and the answer will be -2 and -21. So to rewrite that trinomial, we could say 2x squared minus 2x minus 21x plus 21. Go into some grouping, factor out the 2x, factor out the -21, and we should come to x plus 2, x minus 1, and 2x minus 21. So what does that tell us? We know that our 0 was -2. We also have a 0 at 1 and at 10.5. 21 halves simplifies to 10.5. If we were to go back into synthetic division just to check our work, we could take that 1, put it in the box, bring down the 2, multiply, add again, and we would find that yes, indeed, 1, 0 is a point on our graph. And why not even go that last step, 10.5, if we bring down the 2 and multiply, 10.5 times 2 is 21, and therefore we get a 0 remainder. So therefore, we have zeros at 1 second and 10.5 seconds. How long were we under the ground or below ground level? 9.5 seconds. To get a quick look at this, you can see the function over on the right. The cubic function actually goes from negative to positive infinity, but we know the roller coaster doesn't. The roller coaster goes from 0 to whenever it ends in terms of time. It probably is improbable to think that it's going to start rising as rapidly as it does after 12 seconds, but the red represents the roller coaster ride from 0 to 12 seconds, and we found our answer that it's below ground level between 1 and 10.5 seconds, and you can see that that's represented by the black. So this is a reminder of some of the topics we covered for day 1 and for day 2. Remember, there are tutorials for all of the things we've covered this year on YouTube on our mathematics page. If you have any difficulty with these topics, you might want to go back and watch, or if you want to raise questions with your teacher, these would be good terms to mention. Have a great day.